Jai Hind, welcome to the course Network Analysis and Synthesis, and today we are going to discuss about the network theorems applied to AC circuits. So today topic we are going to discuss two theorems, Thevenin's and Norton's theorem. Why I have taken both the theorems together? Because we know that Thevenin's theorem and Norton's theorems, they are dual to each other. If you understand the working of one theorem, you can easily understand the working of the other one. So today I am going to discuss what is Thevenin's theorem, what is Thevenin equivalent, and how we are going to get the variables in a Thevenin equivalent circuit. By the same way, we are going to discuss about the Norton's, what is Norton's theorem, what is Norton's equivalent circuit, and what are the variables and how we will calculate those variables that we are going to discuss today. So first I am going to discuss about the Thevenin's theorem. So what is Thevenin's theorem? So Thevenin's theorem is basically any two terminal bilateral linear network containing energy sources and impedances can be replaced by an equivalent network containing a voltage source VTH in series with an impedance. So any complex network containing large number of energy sources with their impedances can be replaced by a very simple circuit containing only one voltage source in series with an impedance. And the voltage source is nothing but that is the open circuit voltage across the terminal of the network, and impedance ZTH is nothing but it is the equivalent impedance across the load terminal when we replace all the energy sources by their internal impedances. So how we will get this VTH and ZTH in a Thevenin equivalent circuit? So VTH is the open circuit voltage between the terminals of the network, and the impedance ZTH the impedance measured between the terminals of the network with all energy sources are replaced by their internal impedances. So we can explain a statement of the Thevenin's theorem by this simple circuit. Here we can see that this is a linear active bilateral network containing a large number of energy sources and impedances, and this circuit can be replaced by a very simple circuit VTH in series with ZTH, and this VTH is nothing but open circuit voltage across this terminal. Say suppose this is your A. Suppose this is your A and this is your B. This is the terminal of the network. So we can replace this circuit by this simple one, VTH in series with the ZTH, and VTH is nothing but it is the open circuit voltage across the terminals of the network, terminals of AB of the network, and ZTH is the equivalent impedance of the network as seen from the load terminal. So this is the ZTH, and if we have the independent energy sources, we replace those energy sources by their internal impedances. But we have seen that any network or circuit may contain dependent as well as independent sources. So the circuit may have all the independent sources or combination of independent and dependent sources. So procedure to calculate ZTH in these circuits are different. So first we will discuss the procedure how to calculate ZTH if the circuit is containing only independent sources. Then we will discuss how we will calculate ZTH when the circuit is containing both dependent and independent sources, and in the last, if the circuit is containing only dependent sources, so what will be the Thevenin equivalent and how will find those variables ZTH and VTH. So first, when the network contains independent sources only, so in this case what we do, we replace all the energy sources by their internal impedances, and we find the equivalent impedance between the load terminals. Very simple. Then when the network contains both dependent and independent sources. So in this case there are two methods to find the ZTH. So first is ZTH is VOC upon ISC, and second one is the ZTH is equal to VDC upon IDC. So in the first case what we do, we just find the VTH, which is open circuit voltage. Then find ISC, that is the short circuit current. Short circuit current. So if the network containing both dependent and independent sources, first method to calculate ZTH is take the ratio VOC upon ISC, and the other method is take the ratio VDC upon IDC. What is VDC? VDC is nothing but is a pseudo voltage source we applied across the terminals of the network, across which we are required to find the Thevenin's equivalent. And when we use this second method, that ZTH is equal to VDC upon IDC, what we do, we just put the pseudo voltage source VDC and replace all the energy sources by their internal impedance and take the ratio of VDC upon IDC, we can calculate ZTH. So for the case 2, there are two methods we can find the ZTH. Suppose when the network contains only dependent sources. So if the network contains only dependent sources, we can calculate ZTH by using this expression VDC upon IDC. So there are different methods to find the ZTH depending upon the availability of the dependent and independent sources. So this is very important because we have to, generally a student commits mistake in this case if the network contains both the dependent and independent sources. Now first we will discuss the statement of the Norton's theorem, then we will just take the problems later on. So what is the statement of the network's theorem? We know that the network theorem is dual to the Thevenin's theorem. So we can, if we are able to write the statement of the Thevenin's theorem, we can write the statement of the Norton's theorem. So look at the statement. So any two terminal linear bilateral network containing energy sources and impedances can be replaced by an equivalent network containing a current source equivalent in parallel with an admittance or impedance. If you remember, in case of the Thevenin's, in place of the current source there was voltage source, and in place of parallel there is series. So we know that the voltage source is dual of the voltage source is the current source and dual of the parallel is the series. So just, and the equivalent current source is the short circuit current between the terminals of the network, and the impedance or admittance is measured between the terminals of the network with all energy sources replaced by their internal impedances. So we can see that see there are so many similarity between the statements of these two theorems. We just take the duality of the variables, we can easily write the statement of the Norton's theorem. And procedure to find the your Rn is same for the Thevenin's impedance as well as Norton's impedance. So first just explain the importance of this theorem. So this is a complex network containing so many energy sources with their impedances. This circuit can be replaced by this simple circuit containing only one voltage source in parallel with admittance Yn. So this is the complex, this is the simplest one. So complex circuit can be replaced by a simple circuit. So, this is the short circuit current across the terminals of the network, and this Yn is the equivalent admittance of the network, and to procedure to calculate Yn or Zn is same as we discussed in case of the ZTH. Same. So, here we can see. So, we all it is clear. This first one is clear, second one is also clear. So, in case of the Thevenin, here it was ZTH, here it is Zn. Procedure is same to find the Zn or ZTH. Once we find the Zn, we can find the Yn. Just take the inverse of the Zn to get the Yn. And when the network contains only dependent source, so this is the procedure to get the Zn. Now, we will discuss these theorems with the help of some examples. So, take the first one. This is a network containing only independent sources. There are two independent sources, voltage sources, and you are required to find the current through the this 6 plus j8 ohm impedance using the Thevenin's theorem. So, what we have to do? We have to first draw the Thevenin equivalent. What is Thevenin equivalent? Thevenin equivalent is a very simple circuit containing one voltage source, that is the VTH, in series with an impedance ZTH. So, our approach is to convert this circuit into very simple circuit containing one impedance and one voltage source. So, first we are going to find the VTH. How will find the VTH? This is the coil. So, this is the terminal. We remove this impedance 6 plus j8 ohm impedance from the circuit, and then find the voltage across the this terminal A and B. This is A, and this is B. So, to calculate Thevenin voltage, first and foremost remove the 6 plus j8 ohm impedance from the circuit. So, this is the circuit, and we have to find the voltage across this terminal, and it will be the VTH. So, this is your energy source. So, what is the VTH? VTH will be this voltage 8 into angle 30 degree voltage. Then we know that this is the open. This is open. So, there is no voltage across this minus j5 ohm capacity impedance. There is no current through this. So, voltage is 0. There is no voltage drop across this. So, if we move here, only get this voltage. So, we can find, if we find the voltage across this, we can apply Kirchhoff's voltage law. We can get the voltage VTH. So, first try to find the voltage across 4 plus j3 ohm resistor. So, this is a voltage source, and there is current I, say this current I, and take this current I has only one path. This is open, so no current will flow through this. So, this I will flow through this 4 plus j3 ohm. So, what we do? Just write Kirchhoff's voltage law starting with this terminal. So, suppose this is VA, or VTH is, what is VTH? VTH is nothing but VA minus VB, or you can say VAB. So, start with this terminal. So, VA, there is no drop across minus j5 ohm impedance. So, move from here. So, minus 2 plus, so it is plus 8 angle 30 degree. This is, I think this is plus. Then we can go through this, or we can go through this, because these two elements are in parallel. So, we either can take the voltage across this, or we can take the voltage across this one. Both are same, because both the elements are in parallel. So, just write minus to plus, so 20 minus 2I current through this 2 ohm resistor minus I 4 plus J3. So, I have taken the KVL, I have applied KVL across this loop, and we can get these equations. So, writing this equation, we can get the value of I. So, a value of I will be this much. Clear? All the elements are in series. So, divided with this voltage divided by total impedance 6 plus J3 ohm. So, we can get. So, this is the current having the magnitude 2.98 with angle minus 26.57 ampere. Now, we can apply the Kirchhoff's voltage law either in this loop or outer loop. So, start with this. So, this terminal has voltage say VA. So, VA no drop across minus J5 ohm because this is the open. So, no current will flow through this. So, and plus 8 angle 30 degree, and I have taken this path. So, minus I plus J3 equal to VB, and if we equate, so VA minus VB is nothing but this is the VTS. So, VTS is this much. So, this way we can calculate the, so VTS, what is VTS? VTS is nothing but it is the open circuit voltage across the terminals of the network. Now, the second step is ZTS, because we have to draw this circuit. The final circuit will be like this. Final circuit will be like this, and this is 6 plus J8 ohm impedance, and this is your ZTH, and this is your VTH. And if we find the current I, that is the current that will flow through the 6 plus J8 ohm impedance. So, our job is to find this circuit. Okay, we have got this one. Now, we try to find the ZTH. So, to calculate ZTH, we replaced all the energy sources by their internal impedance if the network is containing only independent sources. So, independent sources, they are ideal in nature, they have the zero impedance. So, zero impedance will be replaced by the zero resistance wire. So, this is the equivalent network, and we have to see from this load terminal. So, if we see from the load terminals, we can see that suppose this is one, this is another, this. So, this 2 ohm and this, they are in parallel. So, they are in parallel with in series minus J5 ohm. So, what we will do, just we find the equivalent impedance of these two branches, and then we take the series. So, this is the in parallel with in series with this. So, this is the ZTH. So, this way we can calculate the ZTH. Now, this is the last step. So, first our object is to get this circuit. To get this circuit, there are two unknown variables, VTH and ZTH. First find VTH, ZTH, draw this circuit and then find the current. So, these are simple. This ZTH in series with this ZL. So, we can ZL is nothing but this is 6 plus J8 ohm. After simplification, we can get this. So, this is the answer. So, the current through this 6 plus J8 ohm impedance will be this one. Now take another example. In this case I have taken one, this is the dependent source, these are the independent energy sources. So which type of this dependent source? It is a voltage controlled voltage source. It is voltage controlled, this source is voltage controlled voltage source. How will you identify? Outside variable, this is the controlling variable. So this is V0. So it is a voltage quantity, and minus plus, this is the polarity of a voltage. So it is controlled by voltage of this branch, V0 here. So this is the V0. So this voltage is controlled by the voltage of this branch, and it is a voltage source. So how will get ZTH? ZTH can be calculated VTH upon ISC. Okay. So first we are going to find the Thevenin voltage, then short circuit current, then we can find the ZTH. So to get the Thevenin voltage, what we do, just replace this impedance from the circuit, just remove it, replace, open it, remove the 6 ohm resistor from the circuit. So this is the network. Look at here. Now the circuit is opened. This is 18 volt. This is the, because this circuit is different from this one. So say this is, if this is V0 dash, then this is automatically it will be twice V0 dash, because voltage of this voltage source is depend upon the voltage of this branch. Then we can apply a Kirchhoff's voltage law on the outer loop. So just write the line equation starting with here. So minus to plus, so it is 18 volt, minus to plus V0 dash, minus to plus twice V0 minus VOC. So VOC is, V0 dash is 3 volt, V0 dash is 3 volt. Now now take the V0 dash is, and V0 dash is 3 volt. How the V0 dash is 3 volt? How will get this 3 volt? Look at here. This 3 ampere current source. Okay. This path is opened. So no current will flow through this. There will be no current. So this 3 ampere current will flow through this branch. Okay. And we can see that the polarity of this V0 dash is, here is minus and here is plus, and for the current direction it will be minus and it will be the plus and minus. Okay. So it is supporting the polarity of the voltage source. It is, so this is 3 ampere current will flow this 1 ohm impedance. So V0 dash is 3 into 1, so it is 3 volt. Okay. Once we get the V0 dash, we apply the, just put the V0 dash in this equation, we can get the VOC, that is the VTH. Clear? Now calculate ZTH. Since the network contains both dependent and independent sources, so ZTH will be VTH upon ISC, or we can say the VTH is nothing but it is the open circuit voltage. upon ISC. So we have calculated BOC. Now we are going to calculate ISC. So this circuit is short circuited. This XY terminals are short circuited. Now we have to find this current ISC. So we can apply Kirchhoff's voltage law in the outer loop. So apply KVL in the loop Y B A X Y. So start with Y to B. So from Y to B we are moving from negative to positive, so it will be the 18 volt. Okay. So plus 18 volt. Then we are moving plus minus to plus. So plus V0 dash plus twice V0 dash. If it is V0 double dash, then it will be twice V0 double dash, because this voltage is depending upon the voltage of this branch. So this way we can calculate V0 double dash, that is coming minus 6 volt. Now apply the KCL at node A. So this is 3 ampere current. 3 ampere current is approaching the node A and ISC current is leaving. So how much current will flow through 1 ohm resistor? That will be the 3 minus ISC. So this current will be 3 minus ISC. Okay. So V0 double dash is nothing but 3 minus ISC into 1. So this is V0 double dash is 3 minus ISC, and we have got the V0 double dash is minus 6 volt. So using these two expressions we can get ISC. Simple. So to get the ISC, what we'll do? We just short circuit the terminals and find the current through that terminal. So ZTH is 27, that is your open circuit voltage divided by 9. So this is 3 ohm using this expression. So first we have calculated ZTH. Now calculate the current through 6 ohm resistor using Thevenin's, because in this circuit we have to apply both Norton's and Thevenin's. So first we are applying the Thevenin's theorem. Thevenin's theorem. So this is your VTH, this is your ZTH, and then connect the 6 ohm resistor. Simple circuit. I is equal to 27 divided by this. Simple Ohm's law. And if you are going to apply the Norton's theorem, you have to draw the Norton's equivalent. So this is the Norton equivalent, 9 ampere. This is your RN, 3 ohm. RN and ZTH both are same. Okay. Because if you draw the dual, this is YN. So YN is dual of the network. ZTH. You take the, it will be admittance. So admittance we have taken the impedance. So this is 3 ohm. So why I have discussed both the theorems together? Because we can understand, in case of the network containing both the dependent and independent sources, you have to find the ISC, you have to find the VTH, and you have to find the ZTH. So this is the Norton equivalent. So this is 9 ampere current through. So if you want to find the current through 6 ohm resistor, so here use current division. Current division rule. So current through 6 ohm resistor will be this impedance divided by this plus this into total current. So total current is 9 ampere, and you will find this is the current through the 6 ohm we can say the I6. So this way we can find the current through the 6 ohm resistor using the Norton's theorem. So this is the basic approach to apply these two theorems. Now take another example. In this case, the network is containing only the independent sources. So, when the network is containing only independent sources, to find the ZTH, VDC upon IDC. So, this circuit can be replaced by this one. So, here this is the pseudo voltage source VDC, and we can see that this is the VAB. So, it will be the VABI by 100. If this is VDC, then this will be the VDC upon 100. So, take the source conversion of this one, this, and this is the simple circuit. So, apply KVL in this loop A, B, C, A. We can write this one, this expression, we can, if you can check it. And here we can see here is the VDC, I1 and IDC, and we are interested to get the ratio of VDC upon IDC. So, what we will do? We just try to find the another equation relating IDC and I1. So, if we apply the Kirchhoff's current law at this node C, we can find the I1. So, I1 plus IDC, I1 is coming through this and IDC is coming, and both are going through the 100 ohm resistor, and voltage across 100 ohm resistor is VDC. So, I1 plus IDC is equal to VDC upon 100. So, we can get the expression for I1, and this I1 we can put here in the above equation. So, on simplification we can get this. So, this is the way to get the Thevenin equivalent, and we know that there is no any independent voltage source. So, if you open the circuit, the open circuit voltage will be 0, because no one is there to supply the power, the energy. So, in case of network containing only dependent sources, open circuit voltage is always 0. So, only we have to find the ZTH, and to find the ZTH we have to apply this VDC upon IDC. Very simple, we have to apply VDC across this terminal here and take the ratio of VDC IDC, we can get the ZTH. So, thank you very much. We stop here. We have discussed networks and Thevenin's theorem using energy sources independent as well as dependent. Thank you. Jai Hind.